Hi everyone. Today I'm going to talk about ARM cores on SmartNIC. ARM cores empower networking on SmartNIC. In my presentation, I will introduce three parts. One is a brief introduction to SmartNIC. The second one is about network offloading models and address the value of ARM cores for the offloading model. Finally, I'll do two full OVS offloading demos. First of all, SmartNIC has become increasingly popular in data center and telco field because, as you can see in the right picture, the SmartNIC support a lot of functions, such as network, cryptography, and storage. SmartNIC also supports a lot of network functions. It supports network overlays. For example, the VXLAN, which is widely used in a public cloud, packet inspection in firewall, and packet processing. Many of them depend on software, so it depends heavily on CPU cores. The target for SmartNIC is to improve network throughput. SmartNIC can increase the network speed, avoid bottleneck, and even sometimes mitigate the DDoS attack, so it can improve the network throughput. It aims to offload network functions from service. Then, secondly, we are talking about the network offloading. So what is a network offloading on SmartNIC? As you can see in the right picture, in a traditional implementation, the traditional NIC, which is called dump NIC, will only receive the packets and send out the packets. It will not parse or process the packets. All the software about processing the network traffic is running on the host. The offloading on SmartNIC is to move the network functions such as the user space virtual switch to SmartNIC. And what is going to be offloaded to SmartNIC depends on the different SmartNIC implementations. Because we offload the network functions to SmartNIC, the SmartNIC will help free host resources and improve performances for packet processing. OVS-DPDK is one of the most common network offloading solutions. The network offloading models, there are a lot of network offloading models, but it can be classified into two classifications. One is a data path offloading, another is a full OVS offloading. In data path offloading, the host will run the slow path and management software. SmartNIC only process the hardware fast path. The SmartNIC only have the hardware fast path. There are two kinds of data path offloading. One is a partial data path offloading. Another one is the other is a full data path offloading. In partial data path offloading, the hardware will do the packet parsing, analyze the packet, and the software on the host will do the flow table lookup and decide which actions to perform, such as drop the packets or forward the packets. In full data path offloading, only the initial first packets for each flow will be sent up to the slow path, and after the rules and identified packets are inserted into the software, the following same packets will not go up to the slow path. It can be processed more fast. As you can see, the software data path and management in both partial offloading and the full data path offloading, those software are running on the host. That means it will take up CPU resources on the host. So let's see what is a full OVS offloading. As you can see in the picture, because the ARM cores on the SmartNIC, we can run both data path and management software on the SmartNIC. The SmartNIC will communicate with the host, will send traffic to the host through SRV or Words.io. Why we need full OVS offloading? Because the computation resources on the host is expensive. Full OVS offloading can free up host CPU computation and cache resources, and it supports latency-sensitive services. In the full OVS offloading, the high-performance ARM cores are available. It supports complex combination of actions when processing the network traffic, and it also supports stateful packet processing. For example, the network state migration. It can migrate the stateful TCP connections. And in SDN, the network topology and network configuration are usually stored in the databases. When one of the databases crashed, the SmartNIC supports fast database recovery through some algorithms. It also supports, because of the high performance ARM cores, it supports high concurrent connection initialization, such as web service. And at the beginning of my presentation, I mentioned the SmartNIC also supports other functions besides network, such as storage and cryptography. Let's see the first full OVS offloading deployment. We use Stingray. The packet generator will generate flows. The flows will go into the SmartNIC through the physical function. When the OVS process on the SmartNIC receive the packets, it will, according to the open flow rule, the OVS process will forward all the packets or the traffic to the virtual machine through SRIOV interface. But in this demo, we will bypass the hardware acceleration function to verify the pure software solutions for OVS offloading. When the virtual machine, the test PMD process on virtual machine received the packets, it will forward back to the OVS process on the SmartNIC. In this way, we can measure the throughput of the software solution for OVS offloading. Let's see the video. First, we need to bring up the physical interface and create a virtual function. We can use a command. We can use this command to see the newly created virtual function. And we bring up the interface. For further configuration and we can use the S tool to check the information for the newly created virtual interface. You can see the bus information, which we will use it to assign the virtual function to the virtual machine. Then we mount the huge page, load the UIO driver. Then we will configure the Stingray SmartNIC. We bring up the interface and create the virtual function with the similar commands. You can see the bus info, the PCI bus info, and the interface name. We bring up the interface. Then we can use a BNXT-CTL to connect the virtual interface on the SmartNIC and the virtual interface on the host. In this way, the SmartNIC and the host can forward packets between them. Then we will mount the huge page and set the number of huge page. Similarly, we load the IGB UIO driver. Because we will use the IGB UIO driver for the interface, we need to unbind the BNXT driver for those interface we need to use. Then rebind the IGB UIO driver for those interface. Then we need to create OVS process on the SmartNIC. We need to avoid interference. We will exit all the existing OVS process. Then we recreate the OVS-DB and start the OVS-DB server. Then we create some interface and bind them to DPDK OVS-DPDK bridge with the interface PCI bus ID. Finally, we'll set the open flow rules to forward the packets from the PF1 to WF0 and the WF0 back to the PF0. Because the configuration are quite long, so I write all the commands to the scripts. After executing the scripts, we need to assign the virtual function we created on the host to the VM. We use the libvirt command to change the to configure the virtual interface for VM. We need to fill the domain, bus, slot, and the function ID according to the bus ID, which we have justly seen. After finish configuration, we can see the bus info here and start the OVS SRLV virtual machine. After the virtual machine is ready, we can use LSPCI to see the commands, to see the interface we just created. And similarly, mount the huge page and set the number of huge page, because we will use test PMD later. And load the driver to help the test PMD process to identify the virtual interface we created. And bind the interface to DPDK and start the test PMD process. Finally, we use a packet generator to send some traffic. We set the frame rate to 15% of the line rate, and with a 64 bytes packet. As you can see, in this configuration, we can achieve 5.5 mega packets per second. Okay, let's see the second demo video. Because in current SmartNIC implementation, there's no implementation includes the up-to-date ARM cores new version N1 with the hardware acceleration function. So I use N1 SDP, which are embedded with a new version N1 CPU, and use a Connect 5 to demo the hardware acceleration. As you can see, the topology for this demo is quite similar to the previous one. And the difference is in this demo we will use a hardware acceleration function in a SmartNIC. Okay, let's see the demo video. First, we can use LSPCI to find out the PCI bus ID for the virtual physical function we need to use, and reset that function, because this will clear all the old configuration to avoid interference. Similarly to the previous demo, we use a similar command to create a new virtual function. We can see the virtual function information, the PCI bus ID. Then, because we need to bind the other driver later, so we need to unbind the kernel driver, Mellanox 5 core, for that for the virtual function. Then we switch the SmartNIC to the switch DV demo, which is necessary for the hardware acceleration function. And we still need to start the OVS function. First of all, we exit all the existing OVS process to clear all the old configurations. Then we use OVS database schema to recreate the OVS-DB and start OVS-DB server. We should attention to the hardware offload parameter. We should set it to true. And also, we need to configure the DV flow parameter to 1, because these two parameters are essential to enable the hardware acceleration functions. To make the above take effective immediately, we need to restart the OVS vSwitch-D process. And then we create three interfaces, PFO, PF1, and VM1, according to the PCI bus ID and the representer ID. Finally, we configure the forwarding rule from PFO to VM1 and from VM1 back to PF1. And we need to assign the virtual interface to use the PCI bus ID to assign the virtual interface to the VM. We configure the domain, bus, and slot and function ID according to the PCI bus ID. And then start the virtual machine. After the virtual machine is ready, we log into the virtual machine. And do the similar, and we can find out the virtual interface bus ID inside of the VM. Similarly, we mount the huge page. Load the driver. because this is essential for test PMD to identify the virtual function we assign to the VM and start the test PMD process. And we use packet generator to send some traffic. With 64 bytes packets, we can achieve 25 million packets per second, which is 4 or 5 times compared to the Stingray performance. According to the 2 demos we have shown, we can say that with stronger N1 CPU and the hardware acceleration, we can achieve high performance on throughput. And in real benchmarking, we also verify the stronger N1 CPU can also achieve high performance when we have high concurrent connection applications like the web servers. But I will not show the demo here because of the time limit. If you have any questions, you can contact me by email. Thanks for your listening.